Welcome everybody to our weekly SEFS seminar. As we have marched our way through the quarter, we're covering all of our faculty who've been promoted over the last year, and happy to have David Butman, who's promoted to Associate Professor in SEFS with a joint appointment also in Civil and Environmental Engineering, as our speaker today. Gives us an opportunity to learn more about our colleagues and what's going on, and looks like a nice plan. David's planned a nice review of and overview of the work going on in his lab. David joined SEFS, does it even say here? It doesn't say here. 2014?
2014.
2014, after a postdoc at USGS and Yale University, and having finished his PhD at the Yale School of Forestry and Environmental Studies, which is now the School of the Environment, right, at Yale. In 2011, completed his master's at Yale in 2006, and a BA at Connecticut College way back in 2000. And so I'm looking forward to hearing David's presentation on the science of carbon from the terrestrial to the coastal to the aquatic ecosystems. Take it away, David.
All right, I'll grab the share. All right, does that look good? Hopefully everyone can see that. Okay, good. So thank you, Dan, for inviting me and letting me at least give some feedback and tell some stories in the SEFS seminar. And today what I'm going to do, it's kind of informal, but what I'm going to do is kind of lay out this growing, what I consider a growing field in trying to link the terrestrial and aquatic and coastal ecosystems from a carbon perspective. And this is kind of being evaluated across this continuum idea. All right. So I'm going to break it down. And if anyone's been in my ESRM 201 class, we're going to start with like a little bit of a refresher on sort of my perspective on how you break down a global carbon cycle into some, very few boxes and lines, for better, for worse. And then I'm going to put that in the context of water, at least my framework of thinking about how water plays a role in this. And I want to touch on, before I start sort of going into the work that I do, I want to touch on some of the ways through time that we've started to account for carbon, excuse me. There's a lot of different terminology, and I have kind of one technical thing I'll go into, but ultimately, those terminologies kind of have evolved over time to sort of evaluate and sum up carbon in different pools and fluxes. And then hopefully, we'll have time to go through some of the stuff that we've been working on for the past few years. All right. So this is where we go back to, at least I consider my ESRM 201 course. And let's just start with probably one of the most common figures when we think about the global carbon cycle right now. And, you can test yourself and looking at this figure. And you should be able to figure out at least what that sort of vertical trend means, right? And all I'm showing here is a snapshot of CO2 in the atmosphere and rising because of anthropogenic CO2 emissions. Hopefully this is not a foreign concept to anyone on the talk right now. But what I like about this version of the figure is that there's so much more information in here. Right? The most obvious thing that you see this broad increasing trend. But if you look a little closer, right, you can see that each of these colors represents different locations where they're measuring CO2 in the atmosphere. And at the same time, you get this sawtooth pattern. And, I always say in 201 that if you can start to interpret this on multiple different levels, you sort of pass the course in my mind. Because that sawtooth pattern, right, and that increasing sort of magnitude of going higher in summer, higher in winter, lower in summer, in northern hemisphere, this relatively muted line in the southern hemisphere, it helps you evaluate at the global scale what's driving changes in carbon. And in this particular case, in the northern hemisphere, we have tons of land, and that's where a lot of our vegetation is. So that's where we have a lot of dynamism in this atmosphere concentrations, whereas you go down south and it's the ocean. and it's a relatively stable but constant balance of carbon. And there's a lot to mix in to this particular figure. And I would argue that, one of the ways that we need to think about accounting of carbon is to sort of tease apart that variability across the globe. All right. So now I want to, oh, sorry, that was a little slower than I thought, break down the carbon cycle into what I consider really simple pools and fluxes. And if anyone's taken a course where they've had to read kind of the IPCC documentation on what it means to actually accumulate and count carbons in all different pools, you'll know that basically this kind of figure would be tons of lines and squiggles up and down from the atmosphere. But I've sort of summed them into major pools right here. And so what I'm showing is, imagine a world before people, pre-industrial revolution. And we had a system, and we're not talking geologic time necessarily, we're sort of talking about that pre-industrial period. We had a system that was relatively in balance. And the units are not necessarily the most important thing I want you to focus on right now. They're in petagrams carbon, or 10 to the 15th grams. But you had a terrestrial system and an oceanic system that basically took up roughly the same amount of carbon that it released through things like metabolism and respiration, and a relatively stable atmosphere. And here I have 590. And you have this kind of slow bleed from the terrestrial landscape out into the coastal ocean, which basically balanced that sort of uptake in the terrestrial ecosystem, then back to the atmosphere. Okay. And so imagine, and then, so the next step is to acknowledge the fact that people actually change the way that we think about carbon in the atmosphere. And I bring up this figure because I think it's really powerful in the way that we think about it. And you can kind of map that original figure of thinking about CO2 and that sawtooth pattern over time onto this kind of same increasing trend right here. But what I like to point out with this is that, in fact, not only do we show again that CO2 is increasing, but we can actually affect it very, I wouldn't say easily or necessarily in the most pleasant ways, but there are forces about our decision making that can actually affect the rate of that increase. And this is produced by the Global Carbon Project, but it's based off of work by Peters et al. On Nature Climate Change in 2012, where they really evaluated the influence of our economic activity on sort of increasing CO2. And this black line is that increasing atmospheric CO2. And at the same time, I think the silver lining from a figure like this, although our rate tends to be increasing over time, is that there are levers that could be changed in our economic activity that could dramatically affect it. But the bigger message here is that obviously we are drastically affecting that CO2 through time. Fossil fuel emissions are not the only component of anthropogenic carbon, and I think it's important to point out, although its relative importance is becoming less and less. Another big component is land use change. And again, these figures come from the most recent products of the Global Carbon Project, where they estimate that, back in the 1960s, land use change was on average around 40% of the total sort of anthropogenic emissions. But fossil fuel emissions have gone up considerably since then, and now that land use change component. And when I say land use change, I guess what I'm saying is, the conversion of forests to other sort of land uses, burning these kind of landscape scale carbon components. Nowadays, it's around 14%, and that proportion is actually decreasing the last time I checked. Okay, so we have these two pieces of anthropogenic carbon that sum to sort of our entire signature of that increasing trend in the atmosphere. And so that's kind of that's my quick kind of overview of what's going on in our atmosphere in the modern times. And now I want to take a second and kind of acknowledge two individuals from my past that got me hooked on even thinking about the carbon cycle. And the first one is George Woodwell. He's right here. And some of you may know some of his seminal work, Woodwell and Whitaker, where they established kind of biomes of the world, really understanding how different ecosystems function based on temperature and precipitation. But more importantly, he was influential in understanding how radiation affects productivity. He actually got most of his money in the early days, and he had in the 1960s and 70s from the Department of Defense, trying to figure out what would happen if you had nuclear radiation affecting forests, and what would happen to productivity and that resource over time. And so they did all these really cool, detailed studies on productivity and thinking about that productivity from a carbon perspective. The second person that I want to acknowledge is Richard Houghton, who goes by Ski. And I directly worked with him when I was at the Woods Hole Research Center. And at the time, I didn't really know anything about him. It's one of those things where when you go on in science and you realize maybe you were working with an important person only after the fact, and you may have ended up regretting some of the things you did during that time, but I digress on that. Regardless, when I was working with him, his whole approach to science was to answer the question of what happens when you change land, use land, manage land, and how you account for the shifts in the carbon stocks over time. And so he basically was a bookkeeper. You know, you can kind of think of him as an accountant, but accountant for carbon. And these two individuals really influenced me in the context of thinking about the processes that affect carbon accumulation, as well as how you start to count it up. And in particular, and this is more a nod to George Woodwell, George Woodwell is really integral in this idea of sort of what is that net accumulation. And I know this might seem like a little bit of too much detail into the carbon cycle, but this is really my only true technical slide that I want to spend one more minute than usual to kind of go through, because I think it sets up the importance of water in the context of thinking about carbon. All right. And again, there's a lot of arrows here. There's a lot of terms, a lot of acronyms, and this is a fault and something that is really frustrating in science, is that we create these figures and you could probably spend weeks trying to interpret it. But I want to point your attention to sort of a couple of concepts here. The first, and what this is trying to depict, is the cycling of atmospheric carbon as it's brought into the biosphere. And again, I encourage anyone to go back to ESRM 201 because we covered this. But nonetheless, we have these terms: gross primary production, net primary production, where you've lost what respiration in autotrophic or in the plant system back to the atmosphere as CO2. And then you have this sort of these trophic components of the ecosystem, consumers that eat the vegetation. And then what happens when the vegetation dies and ends up in the decomposition process. And then eventually what you have is what's left over. And what's left over kind of enters into this really lovely brown circle. It's termed sort of net ecosystem production. And to some degree, when we start to count carbon in the landscape, this is where some people stop. You have to account for fire, right? You have to count what burns away over time. But what you start to do is look at the accumulation of carbon in the soils, the accumulation of carbon in above ground biomass. And if you're a little bit more advanced, you might start to acknowledge that carbon is exported. But in general, and back in the 2006, this export term was what might be harvest, right? It might, if you're on a farm, this is what you pull off as organic carbon in your corn, and it moves out of the system. At the same time, this conversation was being developed, Stuart Chapin up in Alaska, the famous ecosystem ecologist, proposed the term net ecosystem carbon balance, which actually is one step farther to understanding what's left over than net ecosystem production. And just to forewarn you, I'm going to give you one more term at the very end of this talk that might take it even one step farther. But nonetheless, I want to bring this idea of net ecosystem carbon balance to the forefront, because this is when you start to consider water. And I've sort of added this term, this water arrow here, explaining that, this export term, yes, it might be what you harvest out of an ecosystem, but it's also what is carried away in streams and rivers, what may move through a lake, or what leaks out of the bottom of soils that this sort of ecosystem production term doesn't necessarily consider. And it's made up of inorganic carbon. Okay, and so why I consider that important, right, is that this is a term that's really important when we think about carbon sequestration. And I know this gets a lot of interest and a lot of discussion now, and I know we're talking about it even in SEFS from the component of how we can manage forests, in particular in the Pacific Northwest, for carbon sequestration. And I argue that you need to take an ecosystem scale approach when you start to think about carbon sequestration in its entirety. And so that includes the soils, that includes the above ground biomass, but it also, you have to spend the time to figure out where are all the flux is out, where is everything being taken away? And this sort of ecosystem carbon balance approach, I think, is really important. And I'm happy to talk about that more in the future. All right, as we wrap up this sort of overview of the carbon cycle, I want to change the discussion from what I had previously talked about pre-anthropogenic to talking about the importance of now considering the anthropogenic carbon. And so now I've added these boxes right here. And the numbers in here reflect only our land use and land covered land use change in fossil fuel emissions. But let me spend a minute talking about this right now. Because when we ultimately think of ecosystem science and from a carbon cycling perspective, when we think about carbon sequestration, we don't necessarily care, well, maybe I'll rephrase that. Maybe I don't necessarily care about how efficient a system prior to anthropogenic influence was. I really care about how efficient it can be now to sort of accommodate the extra CO2 we're putting up in the atmosphere. And that's what I'm trying to depict right here. And so if we just run through these numbers really quick, and again, these numbers reflect the most recent global numbers from the Global Carbon Project, is that we have about 11 petagrams, units of carbon entering the atmosphere, but only half of that, or 44%, is actually accumulating in the atmosphere. And when we think about, I always say this, when we think about ecosystem services, this might be one of the largest ecosystem services that is completely undervalued, is the fact that both the oceans and land take up half of our fossil emissions. It would be nice to be able to put a price on that and get some return. But nonetheless, that is the case. And I would argue, and from the science and from work with in the realm of oceanography, we have what the oceans are able to take up fairly well constrained because that is really driven by chemistry. And there's a lot of rules associated with that that don't necessarily, are not easily violated. And at the global scale, if we know what's accumulating in the atmosphere, and we know what's being taken up in the oceans, by difference, we calculated what must be being taken up in land. And there's a pretty even split between the land and the ocean, and that land carbon term is around 3.1 petagrams of carbon. But this approach is really sort of simplistic. And this is actually the method that the Global Carbon Project uses at the moment, because the community of science around the difficulty of partitioning carbon in a land environment, it's really complex. And there's obviously members of SEFS are working on this. There's an immense community of scientists that are working on where carbon is actually moving around. And this is where I sort of bring forth what I'm trying to figure out as well. If we're going to spend a lot of time figuring out where this carbon is being stored in the land, we also need to understand and actually bring into the conversation those loss terms to figure that out. And I'm happy to take questions on that stuff towards the end of this as well. So now let's switch directions a little bit, and we'll bring in water. And let me just return really quickly. In this figure, I have inland waters here as a big question mark, because really it wasn't until probably 2007 that these inland water systems were even factored at all into our concept of global carbon cycling, because water was essentially thought to just flow off the land and move out to the ocean. And that was the entire process we needed to concern ourselves with. We know that aquatic systems are much more dynamic and connected to the atmosphere these days. And from that perspective, there was this interesting paper that gets a lot of sort of play right now, where they've sort of kept track of all the research that has come up with these aquatic carbon numbers and fluxes since 2007, when there was a seminal paper on that. And the numbers themselves have gone up quite a bit, from 1.5 petagram units to now the understanding is that maybe we have 5 petagrams of carbon moving from landscapes into the ocean. And when you put this in the context of what forests are taking up from our anthropogenic emissions, it becomes really important to consider. if you start to believe these numbers, all right? And so that's that whole framework and this kind of growing, really rapidly growing field of trying to understand the magnitude of carbon that moves through aquatic landscapes has really sort of framed the research and the space that I operate in within SEFS and over the past 6, even 10 years now. And one of the things that I was excited to be part of was the most recent State of the Carbon Cycle report. Because and what happens every 10 years is the US Global Change Research Program and various agencies within the US develop a carbon assessment for all of North America. And this most recent version, we finished up in 2018, included aquatic systems for the first time. And it was really kind of an exercise in trying to figure out if anyone's getting these numbers correctly and then putting all of the pieces together. And I put this up here to just give you a little bit of perspective that, you know, when you're trying to think about aquatic systems, you need to think about scale and you need to think about networks. And you can kind of cull it all down to thinking about various terms. This carbon allochthonous, it's kind of a horrible term that limnologists love to use as well. Basically means what's coming from land, right? And then you have what's lost through the aquatic systems, gas out as CO2 and methane, burial in lakes, these kind of things, and export to the coast. Right? And it's a kind of a very simple framework, but putting this together for the first time was actually really, really difficult. And you know, really the whole idea behind this approach is to construct a mass balance where you come up with numbers that might be coming in from landscapes, and then you come up with numbers that might be coming out of these aquatic systems, and you try and make the numbers match. And I guess my point of putting this particular figure up is to say that this is the realm that these aquatic systems sort of fit into. And so you need to consider all of the sort of terrestrial components of an ecosystem, coastal ecosystems, but in between we have these sort of dynamics, and this is kind of where I'm going with this continuum that links these other more static, I would say at least these static ecosystems together from a carbon perspective. And I know you can't do the math in your head right now, but one of the interesting outcomes of this activity is that we sort of found that when we included these aquatic carbon fluxes, there was more of a balance between what was being taken up in the terrestrial environment and what we're seeing as concentrations being from emissions back to the atmosphere, all right? And so to sort of wrap up this carbon side of the conversation, you know, I'm sort of framing this idea that in order to sort of better understand the efficiency of these natural ecosystems to take up carbon, and especially our fossil carbon, we need to figure out where this sort of 5 petagrams of carbon fits into the whole picture. Okay. And so this is a great figure, right? And you know, this is, probably have seen it before, but you know, it's a great term from Aldo Leopold. You know, rivers, streams, this aquatic network are the gutters down which run the ruins of continents. And argue that those ruins are pretty much made of carbon, okay? And so this is what I'm proposing as sort of a realm and sort of a growing realm in ecosystem science, is thinking about these aquatic systems as continuum. And what I'm showing here, just kind of a hodgepodge of pictures that show essentially what I mean by different aquatic systems. Stream, you sort of have these river systems, urban environments. This is the Columbia River. But the point is, they're very dynamic. They change in size, they scale in size, and they are inextricably linked to the terrestrial environment. And so part of one of the outcomes of that State of the Carbon Cycle report is I had to sort of sum all of the aquatic components together. And this is the framework that I'm going to go through the second part of this talk right now, and kind of sort of give you a little bit of a show and tell of the work that I've been lucky enough to be involved with and work with colleagues on that sort of travels across this entire continuum. And originally, there are numbers in all these arrows, but I would argue there are opportunities and huge uncertainties with all of these different flows of carbon from the atmosphere to sediments, all throughout these types of wet systems. And I know some of them in SEFS are also tackling some of these questions. So let's begin. Hopefully this is fun. So one of the first questions that our group in SEFS tries to tackle, and one thing that I've worked on with students is asking the question, so where is all this carbon coming from, right? We can measure it in the water, but we have to understand its actual source. And I'm gonna use Ted Stetz here as kind of my sort of deep thinker as we go through each one of these questions. Great guy. I'd say moderate deep thinker. But anyway, it's just a good pose. And we're up on an Arctic lake in this particular picture. Okay. So, you know, in 2018, now Dr. Jason James, who I co-advise with Rob Harrison, basically got he was focusing on soils. And if we think about where we would arguably first look for carbon entering into these aquatic systems, we would want to sort of go up into the landscape. And, you know, when water hits a landscape, it's going to percolate down through soils and would naturally move horizontally into the closest stream or through groundwater and accumulate in larger streams and rivers. And so this was a really cool project. We got money from the USDA, the Mac Stennis program, where we were trying to evaluate the water soluble or the sort of mobile component of carbon in soils and differentiate it chemically from that which is kind of trapped both physically and chemically to particles in the soil. And we were able to work both in Brazil and the Pacific Northwest for this particular project. And it involved taking a lot of soil samples, bringing them back to the lab, and evaluating them, extracting carbon from them, and doing sort of fingerprinting techniques through chemistry to differentiate you know, different extraction methods. And what we were able to show is that that component, which is actually extracted by water, is unique. It's very different than what can be occluded onto soil particles. I'm sure if there are soil scientists on this, please don't hang my feet over the fire too hard on this. And then the other component of this particular project was looking at disturbance, and that disturbance is a management effect. Where we were in Brazil, we were looking at eucalyptus and cerrado. Which the cerrado is the more natural system. And one of the other things that Jason was able to find is that sort of we saw, and we were using isotope techniques, looking at radioisotopes, which gives you the age of carbon that you find in any pool. We were able to show that in those unmanaged stands, that more natural, less disturbed stand, you tended to have older carbon. And so you had an accumulation of older carbon across all depths. And this is intuitive sense, right? If you're not turning over the soils to sort of grow various species, you sort of allow it to normally form a soil profile. And so what does that imply, though, is that these disturbed soils basically can export more water-soluble carbon. And the part that is actually exportable tended to be the older portion that's left over. And so really the take-home message from this work, thinking about you know, carbon along this continuum, is that the carbon that is actually available to move through these particular soils tended to be the older component, which, if that is the case with disturbance, you're sort of reducing soils as a potential carbon sink, and that reduction is actually may potentially move into the aquatic network. All right. So that was great. That was sort of summed up in two of Jason's chapters. And if anyone's interested in that, I'm happy to talk more about it. And so now, if we sort of start moving along our top here, I'm gonna use this top framework as through the rest of this talk. We can start to ask the question of like, all right, so if soil, if carbon enters an aquatic system, the next question is, well, what happens along the way? What's going to happen in this particular aquatic environments as we move along? And so I want to highlight another project that's just starting up right now. And this is something that, you know, if there are undergrads that may want to get involved with, there could be opportunities. But we have an NSF macrosystems project trying to address that exact question. And for those of you that aren't familiar with the macrosystems program, it's a program at NSF that is really trying to look at large scale, kind of whole ecosystem scale processes. And in this particular case, we're trying to think about the cycling and movement of carbon from soils directly into the aquatic system. And this is a kind of cool project because we're working with the U.S. Forest Service, we're working with a private company, and we're helping them develop kind of new versions of sensors that measure carbon in aquatic ecosystems in real time. And as well, we're able to do this by using the National Ecological Observing Network, or NEON, that has infrastructure at a number of locations around the US. Just a little bit of background information on this project, because one of the sites is actually in our backyard. We have about 5 core kind of ecosystems or domains associated with this project. And I'm sort of taking on the role of understanding what's going on in the Pacific Northwest, working with NEON. And we're using sort of a former SEFS core research location, the Wind River site. Those of you may be familiar with it. And so we're going to be spending a lot of time down there installing and playing in stream water and using the equipment. But the cool thing about this project is we have a number of different ecosystems involved. And all of these sites have sort of co-located aquatic instrumentation and terrestrial instrumentation where we can actually really constrain the cycling of carbon in high detail. And so this work is going to be taken on by actually a graduate student in civil environmental engineering, Hannah Conroy. And we hope to, in February, get out in the field into our Wind River site and start deploying sensors into the stream network and integrating that work with kind of the flux tower, these sort of eddy covariance techniques to look at how the terrestrial ecosystem is being manipulated. And we anticipate this will take at least 3 years to get some good numbers. So that's cool. So at this point, we're sort of right at that interface, right, of that uplands into the inland water system. Now, if we keep going as we move along, one of the things that we've found becomes really important is to understand what happens when the hydrologic regime changes. What happens when water in the landscape changes? And you know, the project that we have ongoing right now, this is a NASA-funded project focusing on work up in Arctic and boreal environments, where we are designing field-based experimentation, modeling, and satellite remote sensing methods to sort of come up with a way to understand what happens to carbon fluxes and stocks when you flood a landscape. Because one of the anticipated effects of climate change in the Arctic is a changing of where water will actually sit. And this is a picture that I'm showing right here in the Yukon Flats. This is a national wildlife refuge in the middle of Alaska. And what happens, the Yukon River comes through here, and every spring, the ice breaks up and you get ice jams. And those ice jams, basically, it's like putting a temporary dam on a major unconstrained river, and water just spreads out in all directions. And it's so flat that water can stay in that landscape if those ice jams are in sort of the appropriate kind of geographic position. And so this picture right here is showing a flooded landscape, and there are pockets of these all over Arctic and boreal regions, where these are the dead trees. These are sort of aspen, black spruce pockets that are still alive. And so we want to understand what is the sort of landscape scale effects of this kind of event across different regions of the Arctic, and how frequently these might change into the future. And this work has been driven by a number of people. In the past, there was Dr. Matt Bogard, who's now faculty at the University of Lethbridge in Canada. Some of you may know Dr. Catherine Kuhn in SEFS. She just defended recently, and she's done a lot of her PhD up in this region. But now it's being led by Dr. Fenix Garcia-Tigre-Gross, and she's a NASA postdoc in SEFS. So hopefully when we get back, you may see her around. But the idea is that we have these kind of gradients in landscape, and we're going to measure carbon and methane fluxes across this landscape and find flooded and non-flooded landscapes and work with remote sensors to sort of map out how frequently these landscapes occur and what those fluxes may actually look like. And there's opportunities for undergraduates to get involved with that as well, once we're allowed back in the field. Okay, Now let's keep moving down. Let's talk about wetlands. And this one I'm not going to talk about too much because those pesky hidden wetlands are something that Monica Moscow has already given us a nice talk on. And I'm really excited to be involved with her work, thinking about teal carbon or these forested wetlands and looking at how we can reevaluate the carbon storage in these systems in a much more efficient way across landscapes. And Anthony Stewart, who we've sort of met through her talk, is deeply involved with this. But I encourage you, if you have not seen her talk, to go back and listen to it because it's really an exciting project. And then as we keep moving down, this has kind of been an area where there's been the least amount of progress, probably because it is one of the most complex systems to try and evaluate from a carbon perspective. And I have here carbons in the tide. It's one thing to think about an inundated landscape. It's another thing to think about a landscape that gets inundated and drained twice a day, and trying to think about the importance of that movement of that water and carbon in that system. But it's an exciting area for future research. So this is a project that was, we've basically just wrapped up with the USGS and NOAA through the Sea Grant program in California, where the whole point was to work within this tidal framework to constrain the terrestrial aquatic exchange of carbon in this terrestrial wetland environment. And this was exciting because there's this concept of coastal ecosystems being very, very efficient at taking up atmospheric carbon dioxide and storing it in vegetation and sediments. And this is something that's called blue carbon. And so I just mentioned Monica's project, teal carbon, thinking about wetlands. There's black carbon, there's brown carbon, but aquatic systems in general don't have its own color yet. But there's been a lot of, I guess I could have done this along a colored framework as well. But let me get back to this. So the idea is that, these tidal wetlands are extremely efficient at taking up carbon, storing them in sediments, storing them in vegetation, and that is a potential way to protect them with the idea that you can use it as a tool to mitigate against atmospheric CO2 increases and climate change. This was an interesting project too, because it involved a lot of sensors. And what we were able to do is use one of these eddy covariance terrestrial flux systems to get high resolution fluxes in and out of the terrestrial vegetation and soils. And we instrumented this tidal creek right here with a suite of sensors that measured the movements in and out with every tide of different components of carbon. And I just want to show one result from this particular project, because I think it's really informative. And I should say that this is one of only 2 or 3 projects that have attempted to actually come up with this number in a quantitative way. But one of the core messages from this particular project is that, yes, we were able to show that in general, these coastal ecosystems are able to take up at a high rate carbon in the vegetation and sequestering it into the sediments. But once you can start to quantify what comes in and out through the tidal sort of advection of water and loss when the tide goes out, the net of that actually is a net loss out of the system. And if you're trying to think about these systems as really true blue carbon climate mitigation ecosystems, and you're not including these numbers that sort of estimate the loss through the tides, it's sort of really, you're missing a key flux out of the system, and it actually reduced the efficiency of the coastal environment to take up carbon by about 40% when you include these losses through the aquatic system. All right, that was a lot, and I'm going to start to wrap it up and hopefully have some time for some questions. But I thought it'd be kind of interesting to sort of give a little bit of a highlight of where some of the researches that we're doing in our group is starting to move. And as much as I hate to admit it, I would have to argue that people are obviously a big and important player in landscapes these days. And I've tried to avoid thinking about people in my research for a long time. It adds too much complexity. People are difficult. But nonetheless, that's kind of what we're starting to explore. And so am I affecting carbon? And so I have 2 projects I just want to show because there might be opportunities or people are interested in to follow up with. I'm happy to talk about them, but I'm also happy to introduce Ben Miller, who's now an NSF postdoc in our group, who is doing work, again, at the interface of land and aquatic environments, but from the lens of trying to investigate what happens when we stop the flow of rivers. And in particular, he's working in the Mekong system in Southeast Asia and trying to evaluate what happens when you stop the movement of sediments, when those sediments accumulate, when they might create methane and different carbon gases, or they may store carbon in their system, and then exactly how that carbon moves through food webs as an effect of this anthropogenic use of water for different purposes. And so this is pretty exciting. This is just getting started up, and if COVID situations kind of flatten out, we actually hope to send him back to the Mekong, hopefully in the winter, maybe. Anyway, we'll see about that. And then the last project I want to mention is something that we're just getting off the ground, working with the National Park Service. And this is a project that is really framed around this idea of are there pristine systems left around the world right now? And I think a lot of us would argue that no, there are not. And so Gabe Weisser, who's involved in this particular project, new graduate student, he is developing a program to go out and evaluate sort of high alpine lake systems in the Pacific Northwest that we consider relatively pristine. You know, we go hiking and we see these crystal clear lakes that we assume are not being affected by people. But he's taking a genetic approach to look at various biomarkers, you could call them, sort of genetic signatures in the lakes that we can attribute to humans. And at the same time, we're going to start to do a parallel study to think about sort of the changes in water quality over time, and that's going to translate to how these systems are going to basically affect the uptake or release of carbon from landscapes and their connectivity to the landscapes when we sort of adding sampling on to his more genetic approach. This is a totally new realm for me, and it should be pretty exciting to explore with Rebecca Longford and the National Park Service if everything comes through. So happy to take questions on that, and I'm also happy to point you towards Gabe and put him out in front as well. So just to summarize, I would say, so a couple things I'd love for you to take home from today. We've sort of gone through the realm of trying to, or I've tried to stress upon you the importance of actually including aquatic systems and this continuum in the context of counting carbon. Because every time we do, it actually changes the balance of carbon that's stored on land or exported out to the ocean. And this is an important concept when we think about the net ecosystem carbon balance. But one concept that we're trying to put forth in a paper is this idea of a net watershed exchange. Now, and there's a whole sort of field of thinking about forested ecosystems, terrestrial ecosystems. You can cut them up in any way and look at above ground and below ground carbon. But as soon as you put water in the landscape, it only flows one direction. It only goes downhill. And so that unit of the watershed is really important. And it's not necessarily new, but I think it can be brought forth again in this concept of accounting of equality. One thing that's really exciting, and some of the projects I outlined are addressing this, is they're definitely new, really impressive methods that we can start to evaluate carbon in aquatic systems. Some of the sensor work we're doing that's starting to match the technologies that have been developed in terrestrial and especially oceanic systems. And so we're playing a little bit of a game of catch up, but we're catching up pretty fast. And then the last aspect that I'll leave you guys with is that we know that we're changing hydrologic regimes across the planet. And we know that that has both local implications as well as global implications. And so as those change, we have to understand how tightly those sort of hydrologic regimes move material sort of to the coast or out of these terrestrial ecosystems. And that material that I care about is carbon. And so if we're going to do this into the future, we have to understand how those sort of components are going to change. And I think that's it. And I'll say thank you.
Thank you, David. That's quite a tour of ecosystems and carbon dynamics. I'm happy to hear any questions that people might have. Please feel free to put them in the Q&A or in the chat. One question that I have in my mind, having followed the soccer reports and the Global Carbon Project, I'm just curious, in your work, what do you think is the most misunderstood or biggest missed point in sort of common scientific understanding about the carbon cycle at this point? What are we sort of learning? You pointed to the export and that being a big element. Is that it, or is there something else that we're sort of potentially missing that you're thinking about?
I think there's a bunch of different ways to answer that question. You know, to put it in my perspective, you know, I've talked about this aquatic component, and I think in general, you know, this is not one of these enormous terms in our understanding of the cycling of carbon in sort of gross movements, massive fluxes. But it's important when you start to get at the net, and that's the balance of what is stored on land versus what isn't stored, what might be a flux back. So I think there's an important nuance in that space related to when a system turns from a source to a sink, and how important it is for us to think about a forested landscape as a sink when we scale it up to management, right? Like if we're using these systems as our tool, like a real tool, then we got to really get the numbers right. And in a lot of systems, we're at the margin. Like maybe it's a source, maybe it's a sink. And so there's a lot of work to sort of spend getting those numbers right. However, if I take a really wide lens, you know, it's a fossil fuel question. I mean, it's an anthropogenic emission question. I mean, that's been my perspective as it's grown, that you know, the biggest gains and the biggest uncertainties and even the biggest perceptions from a management side is really, they're going to be on a reduction of carbon to the atmosphere.
Right. Yeah, the land management is kind of a transition process. It helps us get some more immediate gains while we work on these bigger questions.
Yeah.
So Megan Halabisky has a question. Megan, I'm going to switch on your ability to talk. If you want to just go ahead and ask the question, it's a lot of words.
Thanks, David. This is such a good talk and really useful to me. And at the NASA Carbon Monitoring System meeting today, this was a hot topic, and it kind of came up for quite a bit of discussion. And you kind of answered the question on your last slide, but I was hoping you could elaborate a little bit more. So it just seems like for all of these different systems, there's different methods and tools used to measure the carbon stocks and fluxes. And I think, you know, from a carbon monitoring standpoint, like how do we monitor it when we're doing these different tools and methods? Like, is there a way to somehow bring this together? I know you addressed this in your last slide, but I was hoping maybe you could elaborate a little bit more.
Yeah, I mean, I'd say I barely scratched the surface of that. And by no means have I been at this for a really long time. But at the same time, I would argue that, and I feel it with limnology or the science of sort of inland waters, oceanography, and terrestrial systems, they've sort of operated and moved forward in research domains not well integrated. And that has led to methodological developments that you cannot sort of move from one system to another, which makes a program like the Carbon Monitoring Systems program at NASA really difficult if you're looking for an integrated approach. I think there are ways now that we're able to at least go out into the field and measure the same number in different systems. But I would 100% argue we can't model it yet. We can't connect sort of the way water flows very effectively across a landscape to the way that the terrestrial ecosystem actually processes carbon and moves it back to the atmosphere and stores it, because those are two modeling communities that haven't built the right program. It's one thing to route water and to think about adjacent pixels and cells and stuff and how they talk to each other. And it's a very different thing to then just use remote sensing or other maybe sort of ecosystem approaches that just look vertically in a pixel or something like that. I don't know if that answers your question, but I guess it gets to the point that I think that we're in a phase now where we're trying to address methodological approaches that actually are uniform across this space.
Yeah, really interesting. I mean, it speaks, I think in your abstract for this talk, you mentioned kind of being one who kind of covers everything and a specialist in none, but maybe we need more of that.
Yeah, I don't know. I can't code up a model right now. That's the problem.
Thanks, Megan. John Bacher has a question. And if I can find you on the list here, John, I can just let you go ahead and ask it. If you want.
Is that working?
Yep.
So David, I was in class and I missed the beginning of your talk. And so you may have already said this, and if so, sorry, I missed it. But you're talking about carbon movement from terrestrial systems into aquatic systems, and I'm curious what the relative importance of that is compared to the other places carbon goes or stays.
Yeah, no, that's very specific to the ecosystem you find yourself in. And there are a growing number, but still few studies that actually do a good job with that. And one of them is actually done in the Pacific Northwest down at H.J. Andrews. And just as an example, there they find that like if you calculate a landscape scale ecosystem production term or storage in the landscape, balancing what's going to the atmosphere versus what's stored in the soils, 6 to 10% of that number is actually lost to the aquatic system. So relatively small.
Okay.
However, similar studies that have worked in peat environments, especially in England and northern sort of boreal systems, the relative importance of carbon storage in the landscape, fluxes to the atmosphere, and what's lost through these sort of water pathways can get up to 30%. And at that point, that's where you really have to rethink how you balance the entire landscape.
Mm-hmm. And is that of the annual production, or is that of the sequestered carbon from previous years?
Yeah, so you bring up a really good point, John, because the timing aspect of this work is really not well constrained. We do these numbers as a best guess annual. At least I would say the work to date has done the best guess at these sort of annual numbers. But there's a huge unknown when you think about things like legacy carbon. That's a term that's used a lot in northern Arctic and boreal systems where you have something might have been stored in permafrost, where it's been stayed in the system for a long time, and figuring out that lag between stored in the system versus re-entered into what you might consider a faster modern carbon cycle, that hasn't been evaluated very effectively across many different systems.
Interesting. Thanks.
Yeah.
So I have a kind of a follow-up question. Maybe you did answer it, but and this probably is system specific too, of the carbon that is exported to the aquatic system, some is buried, some is processed and released. Do we know what the fraction is generally? I mean, is it still sequestered if it exports into an aquatic system?
So the research, my understanding to date is that there's a growing consensus that if you're imagining a river network that includes lakes along its entire pathway, over short annual timescales, about half of carbon from terrestrial ecosystems that goes into the aquatic system is blown off as carbon dioxide. And so it goes through this processing and is reconverted, mineralized to CO2. And then of the remaining, you tend to have a little, the second half, depending upon who you ask, is just going out to the coast. And we're thinking big scales here. But at the same time, there's a growing literature that is looking over longer timeframes of what's stored in lakes and reservoirs in particular. And I think that there's a space in there that's being evaluated right now that sort of really balance that long-term storage term. And I don't have a sense for how that's going to work out right now.
So that at least it sounds like a little more confidence in that half being released back to the atmosphere. So the export, a significant chunk of it is in fact being.
Yeah.
put back in the atmosphere.
Yeah, and we have pretty good ways to trace that from headwaters all the way down to sort of coastal systems.
I'm just sort of chatting here, and if there's any other questions, please feel free to ask. You got a couple of thankses and great talks.
Yeah, that's good.
It was. It's nice to see that bigger view of the work that you're doing. If there aren't any other questions, I'll add again my congratulations and thanks. Oh, here's a question. Oh, is the increase in carbon, Jen Weiss asks, in the water system increasing hurricanes and tsunamis?
No connection, I don't think, on that one.
It's carbon in the atmosphere that's changing circulation patterns and heating the water bodies that is doing that. It's
Yeah.
the temperature of the water more so. Okay.
Well, if anyone else wants to contact me or any of the students that I mentioned in postdocs, please do. You know, it's the more we can get people involved and thinking about this, the better for me. So, thanks.
Great. Thank you. Thanks, everybody. Thanks for coming.
All right. Thank you.
Yep.